In this video, we'll learn how to analyze two-mode networks. First, what are two-mode networks? If a network has two types of nodes, then the network is two-mode. Two-mode networks are also called bipartite networks. Bi means two, and partite means part. What you see on the screen is a dataset of the Supreme Court decision in the Rehnquist Court. The Rehnquist Court was the Supreme Court of the United States from 1986 to 2005, when William Rehnquist served as the Chief Justice of the United States. In the network matrix you see on the screen, we have two types of nodes. Each column represents a justice. We have 9 justices represented in columns. Each row represents a case. So we have two types of nodes, justices and cases. Let's call this matrix as the justice by case matrix. In the matrix, 1 means a justice decision on a case is in agreement with the majority decision. 0 means a justice decision on a case is in agreement with minority decision. Two-mode networks are usually treated as undirected networks. The types are better considered as affiliations. Here is a network visualization of the matrix. On the left, there are red dots that represent cases. They are the rows in the matrix we just saw. On the right, blue square represent the Supreme Court justices. They are the columns in the matrix we just saw. The ties means the justices' decision on cases were in agreement with the majority decision. Now that we've visualized the two-mode network, how to analyze this network? In OneMode network, we can look at the metrics at the network level, such as density and clustering coefficient. We can also look at the metrics at the node level, such as different types of centrality. We can also detect the structural holes, network brokerage, and network closure. But we are now looking at a two-mode network. You can still run those analyses, but the metrics may be very difficult to interpret. To analyze two-mode networks, we can convert the two-mode networks to one-mode networks. Since there are two modes, we can convert the network to two one-mode networks. One network has only justice as nodes. The other network has only cases as nodes. Let's first convert the Supreme Court two-mode network to a justice by justice network. You can use a function in UCINet to convert the network. I'll show you how to use UCINet in a different video. Here is a one-mode network matrix after converting the two-mode network by columns. Do you see the difference between two-mode networks and one-mode networks in matrices? Here, both rows and columns represent the nodes. So in this network, we have only one type of nodes. All nodes here represent justices. So this is a justice by justice matrix. What do cell values mean in the matrix? To interpret cell values, you always go back to the meanings of ties in the original two-mode network. What does the tie represent in the justice by case matrix? 1 means a justice decision on a case was in agreement with the majority decision in the Supreme Court. When we convert the justice by case matrix to the justice by justice matrix, if a pair of justices' decision agreed with the majority decision, we use a tie connecting that pair of justices. So in this justice by justice case, the cell value means a pair of justices' decision on the number of cases that were in agreement with the majority decision. The cell value I point out means Ginsburg's and Rehnquist's decision on 147.5 cases that were in agreement with the majority decision. Point 5 came from the point 5 in the original two-mode network. It means a concurring opinion which agrees with the decision made by the majority of the court, but states different reasons as the basis for his or her decision. With this OneMode network matrix, you can conduct network analysis to explore the relationship among justices based on their decisions on cases. You can visualize the network, you can calculate the network matrix, centrality, and subgroups in the networks. This is a network visualization I created. Node color represents political party affiliation. Node shape represents gender. The thickness of ties represents tie strength. For the layout, I used multi-dimensional scaling. This layout puts nodes closer if they are similar. In this case, similarity is the similarity of the cell values in the matrix. What does the cell value mean here? It means a pair of justices' decision on the number of cases that were in agreement with the majority decision. Which pair of justices' decision has the highest similarity? O'Connor and Kennedy were the closest nodes in this visualization. It means their decisions were most similar compared to other pairs of justices. Let's look at the justice by justice matrix on the right corner. O'Connor's and Kennedy's decision on 254.75 cases were in agreement with the majority decision. Here, you should ignore the cell values on the diagonal in the matrix because those cell values means the justices agreed with themselves. What's more, the OneMode networks converted from the TwoMode networks are always symmetrical. Which pair of justices' decision has the lowest value of similarity? Stevens and Scalia. They are far apart from each other in this layout. This means their decisions were the least similar. If you look at the justice by justice matrix, you see that Stevens and Scalia's decision on only 59 cases were in agreement with the majority decision. We can also convert the Supreme Court two-mode network to a case-by-case network by using UCINet. Here is a one-mode network matrix after converting the two-mode networks by rows. Rows in the original two-mode matrix represent cases. Here, both rows and columns represent the nodes. So in this network, we have only one type of nodes. All nodes here represent cases. So this is a case-by-case matrix. What do the cell values mean in this matrix? Earlier in this video, we learned that to interpret cell values, you always go back to the meaning of the ties in the original two-mode network. What does the tie represent in the justice by case matrix? 1 means a justice decision on a case was in agreement with the majority decision in the Supreme Court. When we convert the justice by case matrix to the case by case matrix, if a pair of case, that is case A and B, had the same justice's decision agreed with the majority decision, we use a tie connecting that pair of cases. So in this case-by-case matrix, the cell value means the number of justices whose decisions on a pair of cases were in agreement with the majority decision. The cell value I point out means case OKL 95 and ADA 95 had 4 justices whose decisions were in agreement with the majority decision. With this case-by-case matrix, you can then conduct a network analysis to explore the relationships among the cases. Since I'm not a legal scholar, it would be difficult for me to interpret the results. I'll leave the analysis and interpretation to those who are interested. To analyze two-mode networks, you can also conduct core periphery analysis to identify the justices and cases that are core at the two-mode networks. You can conduct this analysis in UCINet. Here are the results. On the left, you see a blocked matrix. The number 1 means good fit. The justices and the cases are a good fit of this core periphery model. And 0 or blank space means bad fit. The blocked matrix has 4 blocks. Since there are 376 cases, it's a very long matrix. I only show the top 2 blocks. The block I point out in red arrows is the core of the network because it has many ones, meaning 3 justices, Rehnquist, O'Connor, and Kennedy, and their decisions on the cases you see on the screen were in the core of the two-mode network. This result is consistent with our previous analysis on the relationships among the justices. The results of the core periphery analysis also includes a density matrix. The core block has the highest density, 0.960. The other 3 blocks are considered as peripheral blocks. The block on the upper right has a density of 0.630, meaning the peripheral justices' decision on the core cases were less frequently in agreement with the majority decisions. The most peripheral block is in the lower right. Its density is the lowest, 0.597. In this video, we learned how to analyze two-mode networks. I'll show you how to use UCINet to run the analysis in a different video.